Hi, today I'm going to demonstrate an application of a decentralized partially observable Markov decision process in a real-time strategy game called StarCraft. This demo is brought to you by myself, Christopher Jackson, and my colleague, Kenneth Bogert. Oftentimes, there are problems involving two or more agents who all have to cooperate together in order to achieve a goal. However, each agent makes his own independent private observations, while at the same time, they all have to contribute to obtaining the highest possible share reward. A decentralized partially observable Markov decision process is used to model such problems. However, it has been shown that these types of problems may have very high complexities in both time and space, even doubly exponential in finite horizons in some cases, making these problems intractable. One approach which tackles these complexities is the JESP, or Joint Equilibrium-Based Search for Policies, an algorithm which uses dynamic programming techniques to build up policy trees more efficiently and is very good at finding locally optimal policies. This is the technique we will use to implement and demonstrate in-game. StarCraft almost needs no introduction, as it's one of the most popular games in the world. Having been released more than 10 years ago, the modding community has been busy at work finding new ways to interact with the game. In fact, they've come up with what's called the Root War API, which taps into the game's internals and exposes an API for developers to create custom AI bots for the game. This is the interface we will use to implement our custom AI bot. There will also be a competition between AI bots at the AIIDE 2010 conference. There is C++ software called the Multi-Agent Decision Process Toolbox, or MADP. It provides an API for conducting scientific research and decision theoretic planning and learning in multi-agent systems. It has several algorithms, including DEC-POMDP algorithms and a model interface. It is currently only for Linux, but in our research we create a Windows port so that we may easily build a Windows DLL to be injected into StarCraft. We will demonstrate a JESP-based algorithm in StarCraft, as well as provide our own DEC-POMDP model and compare against an ad hoc brute force approach. We will evaluate the AI based on the number of team members that survived and the number of enemy combatants eliminated. Here's a list of references which includes papers and links to the tools mentioned in this presentation. Before we demonstrate our AI bot in game, let's first take a quick peek at our DEC-POMDP model. Here's an example we used to model a problem which consists of 2 Dragoon units which will be controlled by our AI versus a 2 times upgraded armored enemy Ultralisk. You will first notice that our optimality criterion includes an infinite horizon with a discount factor of 0.9. We have 8 states, where the first digit expresses whether or not Unit 1 is being attacked, the second digit Unit 2, and finally the third digit showing if the enemy is being attacked. For example, state 101 shows Unit 1 being attacked, Unit 2 not being attacked, and the enemy also being attacked. Each agent has 2 actions, attack or escape, making 4 possible joint actions. There are also 2 observations for each agent, see the enemy or don't see the enemy. Then we move on to our transition matrix, which shows the probabilities of moving from one state to the next given the joint action in the current state. Similarly, we have an observation matrix, which shows the probabilities of having a particular joint observation given the joint action and the state. And finally, we have our reward function, which expresses the reward given to the team based on the state and the joint action. For example, here, if Unit 1 will attack and Unit 2 will escape because Unit 2 is being attacked, then that's a good thing, and that's a reward of 100. However, in the same scenario, if Unit 2, who is being attacked, decides to keep attacking head-on, and his partner, Unit 1, runs away, then that's very bad, hence negative 100. Here's a slightly different model which has 3 states and uses the concept of being in a winning, neutral, or losing state, where the observations model the units being attacked. We are first going to show what would happen in a brute force always attack scenario, as in the previously discussed problem. This is not AI controlled. We want to see what happens when we do a head-on attack of these 2 Dragoons versus a Zerg Ultralisk. You will notice that the Zerg Ultralisk is upgraded twice in armor. This sort of head-on attack with these 2 Dragoons, they prove to be too weak for this powerful opponent. Close, but inevitably losing every time. Now we will show our implementation of JESP within StarCraft. We will demonstrate the same scenario, but this time we will use artificial intelligence to try to take on this powerful opponent. The JSP planner has been initialized using length 5 horizon, and the value of the joint policy tree is displayed. Our AI engaged the enemy. However, looking at the output, you'll notice that the two units decisively switches between attack and escape in order to maximize the team's joint reward. Our AI is successful in their attack and is able to keep both team members alive. Here we demonstrate another scenario where we used our 2-unit model but applied it pairwise to 12 zealots versus another 12 zealots controlled by the built-in CPU AI. The CPU AI is the purple team. You'll notice that our AI tends to stick closer together as well as cluster around enemy forces. In the top left hand corner of the screen, you'll also notice that we have how many units are remaining, and how many units are under attack, and how many units are attacking. Again, our AI succeeds with 6 units remaining. That was pretty exciting. Let's try that again, but this time with 12 dragoons. Pay attention to the high ratio of the number of units attacking versus the number of units under attack. We're successful yet again with 7 units remaining. This concludes our presentation of applying a deck POMDP based algorithm in a real-time strategy game. Thanks for watching.